Tonight, reaching Pluto can be easier than flying over the Sun, because in space the longest journey is not always the hardest one. Pluto is so distant that sunlight takes hours to cross the gap between it and Earth. The Sun is our next-door star, only one astronomical unit away. If distance were the main thing that made spaceflight difficult, there should be no contest. A spacecraft aimed at the Sun ought to have the easier trip. But one of the strangest missions ever sent toward our star did something that seems almost absurd. It went to Jupiter first. The spacecraft was Ulysses, the joint mission of the European Space Agency and NASA. Its goal was not to dive through the Sun's corona. It was to leave the broad, flat plain where the planets travel and pass over the Sun's polar regions. Ulysses launched in 1990, reached Jupiter in 1992, and used the giant planet's gravity to bend its path out of the ecliptic. Only after travelling outward toward Jupiter could it return inward on an orbit that carried it beneath the Sun's south pole and then above the north. Years later, New Horizons would also race past Jupiter, but its destination really was in the outer darkness. Jupiter increased New Horizons' speed on the way to Pluto, helping the spacecraft reach the dwarf planet in 2015. The two missions used the same giant planet for almost opposite reasons. One used Jupiter as a slingshot toward a world billions of kilometers away. The other used Jupiter as a steering wheel so it could fly over the poles of the star beside us. And by the end of tonight, you're going to understand why a spacecraft can travel outward toward Pluto more naturally than it can climb above the Sun, why Ulysses had to visit Jupiter to reach the solar poles, and why the real map of spaceflight is drawn in velocity rather than distance. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing we need to remove is an image that feels obvious but is physically wrong. When we picture a spacecraft leaving Earth, it is easy to imagine it starting almost from rest, choosing a destination and firing its engines toward that destination. The Sun is inward, Pluto is outward, so perhaps the closer target should require less work. But a spacecraft on the launch pad is not standing still with respect to the Sun. Earth is already moving around the Sun at roughly 67,000 miles per hour, or about 30 kilometers per second. Everything on Earth shares that motion, and when a spacecraft leaves Earth, it does not leave that enormous sideways velocity behind. It carries the motion with it. That single fact changes the entire map. Earth does not avoid falling into the Sun because the Sun's gravity is weak. It avoids falling in because Earth is moving sideways fast enough that, as gravity bends its path inward, the planet keeps missing the Sun. An orbit is a continuous fall that never reaches the center. A spacecraft leaving Earth begins inside that same fall. This is why getting close to the Sun is already harder than the simple picture suggests. Parker Solar Probe did not merely point toward the Sun and let gravity do the rest. To lower its orbit dramatically, it had to get rid of a large part of the sideways motion inherited from Earth. The mission used repeated flybys of Venus to remove orbital energy and draw its path progressively closer to the Sun. And that solved one kind of problem, but flying over the Sun introduces another. To see the solar poles from high latitude, a spacecraft must leave the plane in which it inherited almost all of its motion. It is not enough to change how fast the spacecraft is moving around the Sun. The direction of that velocity has to change as well. Velocity is a vector. It has a speed and a direction. A rocket therefore pays not only when it speeds up or slows down, but also when it turns its velocity in a new direction. If the turn is large and the spacecraft is moving quickly, the cost can become enormous. Imagine an arrow, almost 30 kilometers long, representing the distance Earth travels through space every second. That arrow lies nearly in the flat plane of the planetary system. A conventional journey toward the outer planets can reshape that arrow while keeping much of the motion in roughly the same broad plane. A true solar polar journey asks for something more radical. It asks us to tilt the arrow upward. This is where distance stops being a useful measure of difficulty. Pluto is far away, but much of the task of reaching it is an energy problem. Give a spacecraft enough heliocentric energy in the right direction, and its orbit can stretch outward across the solar system. New Horizons left Earth at the highest launch speed yet achieved relative to Earth, and later gained additional speed from Jupiter. The journey was long, but the basic direction of travel worked with the flattened architecture of the planetary system. Ulysses faced a different geometry. It needed an orbit that cut steeply across that architecture. And there is an important correction here. Saying that flying over the Sun is harder does not mean Ulysses simply launched faster than New Horizons. It did not. New Horizons departed Earth faster. The difficulty we are isolating is the cost of changing the orientation of a heliocentric orbit, not a contest between launch speed records. That is precisely why Ulysses is such a powerful example. The mission did not beat the plane change problem by carrying an impossibly large tank of propellant. It borrowed a planet. At Jupiter, the spacecraft encountered a gravitational field powerful enough to redirect its path dramatically. In the Sun-centered frame, Jupiter changed the orientation of Ulysses' velocity and threw the spacecraft out of the ecliptic. The result was an orbit that would have been extremely costly to create directly with onboard propulsion. So the mission to look down on the Sun first travelled away from it. That is not a detour around the problem. It is the solution. And once we see that, the solar system begins to look different. The flatness of the planetary system is not merely a pattern in astronomy textbooks. For spacecraft, it is an inherited direction of motion, an invisible track. Travelling far along that track can be easier than leaving it. This is also why modern solar missions can sound similar while solving different pieces of orbital mechanics. Parker Solar Probe went extraordinarily close to the Sun by reducing orbital energy with Venus. Solar Orbiter is using planetary flybys to increase its viewing latitude step by step. One mission pushes inward, the other also works upward. The deeper question is no longer why Pluto is far away or why the Sun is hot. It is why turning an orbit is so expensive. To answer that, we need to stop drawing the solar system as a set of circles around the Sun and begin drawing it as a field of velocity arrows. Once we do, one of the strangest routes in space exploration becomes almost inevitable. To fly over the Sun, Ulysses first had to go the wrong way. That wrong way only makes sense once we see just how flat the solar system really is. Most diagrams hide this from us. We usually meet the solar system from above. The Sun sits in the center, the planets trace a family of rings, and the whole system spreads across the page like the grooves on a record. From that angle, distance dominates the picture. Mercury is close, Neptune is far, Pluto is farther still. But turn the picture 90 degrees. Now almost everything collapses toward a thin line. The major planets do not orbit the Sun on randomly tilted paths. Their orbits lie close to a common plane astronomers call the ecliptic, defined by Earth's orbit around the Sun. Viewed from above, the planetary system looks broad and enormous. Viewed edge-on, it looks remarkably compressed. That flatness is not an accident of the present-day solar system. It is a fossil of how the solar system formed. More than 4.5 billion years ago, the material that would become the Sun and planets belonged to a collapsing cloud of gas and dust. As that material collapsed, it spun and flattened into a protoplanetary disk around the young Sun. Within that disk, matter gathered into larger bodies. The planets inherited the disk's broad direction of motion and its broad plane. The modern solar system is not perfectly flat. It never was a sheet of paper. Planetary orbits have small inclinations relative to one another, and smaller bodies can follow much more tilted paths. Pluto itself is a conspicuous example, travelling on an orbit tilted about 17 degrees relative to the ecliptic. But the architecture remains unmistakable. The 8 planets circle the Sun in the same general direction and stay remarkably close to the same broad orbital plane. Their paths form something less like a swarm and more like lanes around a common track. That track is the first hidden structure behind our title. Because spacecraft do not begin their journeys outside it, they begin on a planet embedded inside it. Imagine standing far above the Sun's North Pole and watching the system in accelerated time. Mercury would race around the center, Venus would follow, Earth would circle farther out, then Mars, Jupiter, Saturn, Uranus, and Neptune. Each would move around the Sun in the same overall sense, their orbits nested inside one another. Now lower your viewpoint until you are almost level with Earth's orbit. The grand circles narrow. The planets that once seemed scattered across an enormous two-dimensional map gather close to a common horizontal band. The geometry has changed, but more importantly, our intuition has changed with it. A spacecraft headed from Earth toward Mars, Jupiter, Saturn, or Pluto begins inside that band. Its target may be astonishingly distant, and reaching it may require enormous energy, careful timing, planetary flybys, and years of flight. But the destination still lies broadly within the traffic pattern the spacecraft already occupies. A solar polar trajectory asks for a different kind of departure. It asks us to leave the traffic pattern itself. This distinction can feel almost trivial in a drawing. If an orbit is a line on a page, we can simply tilt the line with a pencil, rotate it 20 degrees, 40 degrees, 90 degrees. Nothing resists us. Nature does not grant that freedom. An orbit is not a geometric ring suspended in empty space. It is the path produced by a moving object's velocity under gravity. Changing the plane of that orbit therefore means changing the direction in which the object is moving. That is why the flatness matters. The ecliptic is not a wall. There is no physical surface a spacecraft must punch through. Nothing dramatic happens at the moment a probe crosses from one side of the plane to the other. There is no boundary marker, no pressure change, no layer of material blocking the way. The barrier is momentum. Every launch from Earth starts from a world already participating in this ancient, flattened circulation around the Sun. Before a rocket ignites, before a spacecraft separates from its upper stage, before mission controllers begin a deep space cruise, the vehicle is already part of that motion. It is carried around the Sun because Earth is carried around the Sun. That makes the solar system's flat track more than an astronomical curiosity. It becomes a starting condition. And starting conditions matter enormously in spaceflight. Suppose we wanted to travel from one city to another on Earth. We might care mainly about distance. A trip of 100 kilometers is usually easier than a trip of 10,000. But imagine instead that we are already riding an immense moving platform, and nearly every destination of interest is moving with the same platform in roughly the same direction. A distant point along the platform could require a long journey, but at least much of our existing motion belongs to the same system. Now imagine that our destination is directly above the platform. The geometric distance might be smaller, but reaching it requires changing a motion we already possess. This analogy is imperfect, because nothing in orbit is actually riding a solid surface. Yet it captures the important reversal in orbital mechanics. Where we already are is not defined only by position. It is also defined by motion. That is why a map showing kilometers can mislead us. Two spacecraft can depart from the same planet and face profoundly different problems, even when one destination is physically much farther away. One trajectory may mostly reshape an orbit within the familiar planetary plane. Another may require rotating that orbit away from the plane itself. And this is where Ulysses becomes stranger. Its route to Jupiter was not simply a way to gain speed. The mission needed access to a massive body whose gravity could redirect its heliocentric trajectory far out of the ecliptic. Jupiter offered a way to transform the inherited geometry rather than fight it entirely with propellant. The flat track had finally become an obstacle, but we have not yet reached the deepest reason. We have described where the planets move. We have not yet accounted for how much motion Earth gives a spacecraft before the mission even begins. That inherited motion is enormous. And once we put a number on it, the difficulty of flying over the Sun stops looking like a strange engineering inconvenience and starts looking almost inevitable. So before we ask how to turn an orbit upward, we need to answer a more basic question. When a spacecraft leaves Earth, how fast is it already moving around the Sun? The number waiting underneath that flat track is almost 30 kilometers per second. That is Earth's average speed around the Sun, 29.78 kilometers every second. It is easy to hear that number and let it pass as another piece of astronomy, so make it physical. In a single second, Earth moves almost 30 kilometers along its orbit. In 1 minute, it travels nearly 1,800 kilometers. During the few minutes it takes to launch a spacecraft through the atmosphere and begin climbing away from Earth, the planet itself has already swept thousands of kilometers around the Sun, and the spacecraft goes with it. This is the starting velocity that ordinary maps leave out. A rocket standing motionless on a launch pad is motionless only relative to the ground beneath it. Relative to the center of Earth, it is also moving because Earth rotates. Relative to the Sun, it is moving much faster still, carried along with our planet at roughly 67,000 miles per hour. Nothing about launch erases that motion. When the engines ignite, the rocket does not begin from zero on some universal speedometer. Its engines change a velocity the spacecraft already has. Once it escapes Earth's immediate gravitational control, the important question becomes how that new velocity compares with the motion Earth was already carrying around the Sun. This is where orbital mechanics begins to feel less like travel and more like editing an existing trajectory. The spacecraft is not choosing a path from scratch. It is inheriting one. And the easiest way to understand that inheritance is to stop thinking of Earth as something being held up by empty space. Earth is falling. The Sun's gravity is pulling it inward every moment. If Earth somehow lost its sideways motion while remaining at the same distance, gravity would no longer have to bend an orbit. Earth would begin falling toward the Sun. But Earth does have sideways motion, and it has a great deal of it. During every moment that gravity pulls the planet inward, Earth advances sideways. The direction of its motion changes continuously, but the planet keeps missing the Sun. That is an orbit, a fall with enough sideways speed that the surface you are falling toward keeps curving away from your path. The same basic picture works for a spacecraft. After leaving Earth, a probe does not simply float free of the solar system's motion. Unless its engines or a planetary encounter change things, it continues around the Sun with a velocity closely related to the one it inherited at departure. This gives mission designers a powerful starting point, but it also gives them a constraint. If you want to travel farther from the Sun, one useful strategy is to add heliocentric speed in roughly the direction Earth is already moving. The spacecraft enters a new solar orbit with more orbital energy. The far side of that orbit can then stretch outward. If you want to travel closer to the Sun, the intuitive move is almost the opposite. You must remove some of the sideways heliocentric motion so gravity can pull the spacecraft into an orbit with a lower perihelion. This is the trap hidden inside the phrase "fall toward the Sun." Gravity is already pulling. The difficult part is getting out of the way. NASA used exactly this idea when describing the challenge faced by Parker Solar Probe. A spacecraft leaving Earth begins with roughly 67,000 miles per hour of sideways motion around the Sun. Parker did not need to erase all of it, because its goal was to pass extremely close to the Sun rather than fall directly into it, but it still needed to shed about 53,000 miles per hour of that inherited sideways motion. A rocket could try to perform an enormous braking maneuver. Parker used a more elegant method. Venus. Each carefully arranged encounter allowed the planet's gravity to alter Parker's heliocentric orbit. Across repeated flybys, the spacecraft gave up orbital energy and drove its perihelion deeper into the Sun's gravitational well. Notice what has happened to our original picture. The Sun did not become difficult because it was far away. It became difficult because Earth gave Parker too much of the wrong motion for the orbit Parker needed. That distinction matters even more for a solar polar mission. Imagine the heliocentric velocity of Earth as a long arrow tangent to its orbit. Its length represents almost 30 kilometers per second. Its direction lies nearly inside the ecliptic plane we built in the previous part. A spacecraft leaving Earth receives that arrow before its own mission-specific changes are added. For a journey toward the outer solar system, mission designers can work with much of that direction. They can increase the energy, reshape the solar orbit, and use planetary encounters to stretch the path outward. The spacecraft may travel for years, the distances may become enormous, but much of the motion still belongs to the same broad orbital architecture. For an inward journey, the arrow must be shortened in the heliocentric sense. For a polar journey, something more severe is coming. The arrow must be turned. That sounds like a small linguistic difference. It is not. Imagine a car moving rapidly east. Slowing it is one problem, speeding it up is another. But suppose you want the car to continue at nearly the same speed while suddenly travelling north. You have not merely changed the number on the speedometer, you have replaced one velocity with another. Spacecraft face the same vector logic, except there is no road providing friction and no ground supplying the force of the turn. Every deliberate change must come from propulsion, gravity, or some other physical interaction. And the faster the spacecraft is already moving, the more expensive a large redirection can become. We are not going to calculate that cost yet. First, there is a more important realization. The nearly 30 kilometers per second inherited from Earth is not just free speed, it is directional commitment. It points along the planetary system. That is why Pluto can be enormously distant without requiring us to rotate the spacecraft's orbit through anything close to 90 degrees. Pluto's own orbit is tilted relative to Earth's, but the journey still belongs broadly to the same flattened family of motion. The Sun's poles do not. To rise far above them, a spacecraft must acquire a large component of velocity perpendicular to the ecliptic. It has to transform motion that began mostly sideways around the Sun into motion that carries it steeply across the solar system's plane. Now Ulysses' journey to Jupiter becomes less mysterious. Jupiter was not simply far away enough to provide a dramatic slingshot. It was massive enough to help change the direction of the spacecraft's heliocentric velocity without requiring Ulysses to produce that entire change with its own engines. But before we let Jupiter solve the problem, we need to see how bad the problem really is. We now have the hidden starting number, about 29.78 kilometers per second. We know where that velocity points. Along the flat track, the next step is to separate two ideas that everyday language often blends together: speed and velocity. Because once direction enters the calculation, turning an orbit toward the Sun's poles stops looking like a simple climb. It becomes one of the most expensive turns in the solar system. Speed tells us how fast something is moving. Velocity tells us something more important: where it is moving. That difference sounds almost too simple to matter. On Earth, we often use the words interchangeably because the distinction rarely changes our intuition. A car traveling 60 miles per hour is traveling 60 miles per hour whether it is heading north or east. But in space, changing north to east can be as important as changing 60 to 100. Sometimes more important. Return to the velocity arrow we built around Earth. Its length represents speed, roughly 30 kilometers per second around the Sun. Its direction points almost along the ecliptic. If we make that arrow longer without changing its direction very much, the spacecraft gains heliocentric orbital energy. Its path can stretch farther from the Sun. If we make it shorter, the spacecraft loses orbital energy. Its orbit can fall deeper toward the Sun. But if we rotate the arrow, we are doing something fundamentally different. We are changing the plane of the orbit. And that distinction separates the road toward Pluto from the road over the Sun. Imagine three spacecraft leaving Earth from nearly the same place. The first accelerates in roughly the direction Earth is already traveling around the Sun. Its new velocity is larger. The spacecraft moves onto a solar orbit with more energy. Instead of remaining near Earth's distance, That orbit can extend farther outward before the Sun's gravity turns the spacecraft back. The second spacecraft changes its heliocentric motion in the opposite sense. It removes some of the sideways speed Earth gave it. Now the spacecraft no longer has enough tangential motion to remain on an Earth-like orbit. Its path bends more deeply inward toward the Sun. The third spacecraft faces a stranger request. Keep much of the speed, but send the trajectory far above the ecliptic. That means creating a large velocity component in a direction the spacecraft did not previously possess. The first two problems mostly change the size and shape of the orbit. The third changes its orientation in space. These are not equivalent jobs. To see why, forget spacecraft for a moment and picture two arrows drawn from the same point. One points east, one points north. Suppose both are exactly the same length. The speed represented by them is identical, yet the velocities are completely different. To transform the eastward velocity into the northward velocity, we cannot simply say that the speed stayed constant and therefore nothing changed. Physically, something had to remove the eastward motion while creating northward motion. The spacecraft must acquire the difference between those two arrows. That difference is what propulsion has to pay for. This is one of the places where human intuition breaks badly. We see a spacecraft moving at 30 kilometers per second and imagine that turning it 90 degrees should merely redirect the motion it already has. A rocket cannot simply grab an existing velocity arrow and rotate it for free. Thrust adds a new velocity change. Gravity during a carefully designed planetary encounter can also redirect the trajectory. But some force must perform the turn. Without that interaction, an object continues moving according to the trajectory it already has. This is why spacecraft navigation is built around changes in velocity rather than around distance traveled. Engineers usually describe those changes with a quantity called delta V. Delta means change. So delta V is a change in velocity. Sometimes that change makes a spacecraft faster, sometimes slower, sometimes it primarily alters direction, and sometimes it does several of those things at once. This is the currency of orbital maneuvering. Not kilometers, not travel time, velocity change. A mission can cross billions of kilometers while spending relatively little additional delta V after departure. Once a spacecraft has been placed onto the right trajectory, gravity can carry it across immense distances for years. The engines do not have to push it across every kilometer. That is one of the great mental reversals of spaceflight. Distance can accumulate almost for free. Changing the trajectory does not. Consider a spacecraft coasting toward the outer solar system. Once it has enough orbital energy, the Sun's gravity gradually slows its outward motion. But the spacecraft keeps traveling. The emptiness between the planets does not act like a road that must be continuously powered through. There is essentially no atmosphere imposing a constant drag penalty. A long coast can therefore be very long without requiring a proportional amount of fuel. This is why asking how many kilometers separate two destinations tells us surprisingly little about how difficult the transfer will be. The better question is this: what velocity does the spacecraft have now? And what velocity does it need? That is the real map. And on that map, Pluto begins to lose some of its intimidation. Not all of it. Reaching Pluto required extraordinary launch performance, precise navigation, years of flight, and a carefully designed encounter with Jupiter. Nothing about that mission was easy. But Pluto did not demand that New Horizons rotate its heliocentric trajectory out of the planetary system by anything close to a right angle. The dwarf planet's orbit is tilted relative to the ecliptic, but it still belongs to the broad architecture of the solar system's flattened disk. New Horizons could therefore attack the main problem largely by gaining energy and stretching its solar trajectory outward. That is a difficult problem, but it is a familiar one. A solar polar mission is asking for a different transformation. Picture the solar system edge on again. Earth's velocity arrow points almost across the page. Now imagine wanting a spacecraft eventually to pass far above the Sun so that it can look down toward a pole. The spacecraft needs motion that points strongly out of the page. We are no longer merely extending an orbit. We are trying to rotate its entire stage. And the original sideways motion does not politely disappear when we begin thrusting upward. It is still there. That is what makes large inclination changes so unforgiving. We are not starting with a stationary spacecraft and accelerating it in a new direction. We are starting with a spacecraft already racing around the Sun and attempting to replace a substantial fraction of that directional motion with another. This also explains something that will become crucial later. The cost of turning an orbit depends on how fast the spacecraft is moving when we try to make the turn. If the velocity arrow is very long, moving its tip through a large angle requires a large change. If the arrow is shorter, the same angular turn can require less. That principle will eventually explain why mission designers sometimes travel to seemingly inconvenient places before changing an orbit. It will explain why the outer solar system can become useful to a mission whose scientific target is the Sun. And it will explain why Jupiter was not merely a convenient planet for Ulysses. It was a way around a terrible bill. But first we need to understand the other side of the comparison. Pluto. New Horizons reached a world so remote that its voyage lasted nearly a decade. It crossed the orbit of Mars, past Jupiter, moved beyond Saturn, Uranus, and Neptune, then continued into a region where the Sun had diminished to an intensely bright star in a dark sky. By distance, it was one of the great journeys in exploration. Yet in velocity space, much of that journey followed a surprisingly cooperative idea. Take the motion Earth already gives you. Add energy, stretch the orbit outward, and let gravity carry you across the dark. That is what we need to reconstruct next. Because once we understand how New Horizons reached Pluto, we can put its trajectory beside the solar polar problem and see exactly why billions of kilometers are not the most frightening number in this story. Pluto is where distance becomes almost ridiculous. At the time New Horizons reached it, the spacecraft had spent more than 9 years crossing the solar system. Its path from Earth to the Pluto system covered more than 3 billion miles. By ordinary intuition, that should make Pluto the harder destination in almost every sense. And in many ways, it was hard. New Horizons needed an extraordinary launch. It needed exquisite navigation. It needed a spacecraft capable of surviving nearly a decade between launch and encounter. It needed power, communications, thermal control, and instruments that would still work after years in deep space. But none of those facts changes the orbital lesson. Once New Horizons had been placed on the right outbound trajectory, the emptiness between the planets did not demand that its engines keep pushing it forward. The spacecraft could coast. That word is more important than it sounds. On Earth, long journeys usually consume more energy because motion through air, water, or over roads continuously loses energy to friction. A car crossing a continent cannot receive one burst of speed at the beginning and then glide the rest of the way. The environment keeps taking energy away. Interplanetary space is different. A spacecraft traveling between the planets is continually responding to gravity, especially the gravity of the Sun. But it does not encounter anything like the constant drag of a highway or an atmosphere. Once the launch vehicle and planetary encounters have shaped the trajectory, enormous distances can accumulate during freefall. New Horizons is a beautiful example. On January 19, 2006, its launch vehicle did something extreme. After the spacecraft reached an initial parking orbit around Earth, additional rocket stages drove it onto its interplanetary escape path. New Horizons departed Earth at about 36,400 miles per hour relative to our planet, the highest launch velocity then achieved by a human-made object relative to Earth. That number matters. But the deeper point is what the launch accomplished. The rocket did not need to provide propulsion for every mile between Earth and Pluto. It changed the spacecraft's trajectory once, violently and precisely, so that gravity could take over. Think back to our velocity arrow. Earth had already supplied the large sideways component around the Sun. The launch added the velocity change needed to escape Earth and place New Horizons on a much more energetic heliocentric path. The arrow had been reshaped for the outer solar system. And then New Horizons began to leave. Mars's orbit came and went. Ahead lay Jupiter. This was the next major piece of the trajectory, and it shows why saying that New Horizons simply received one large launch burn would be incomplete. Jupiter was not merely something New Horizons passed on the way. It was part of the propulsion strategy. On February 28, 2007, a little more than a year after launch, New Horizons swept past the giant planet. Jupiter's gravity bent the spacecraft's path through the planet's moving gravitational field. Viewed relative to the Sun, the encounter transferred orbital energy to New Horizons. The spacecraft left moving roughly 9,000 miles per hour faster toward its distant destination than it otherwise would have. The practical payoff was enormous. The Jupiter encounter shortened the voyage to Pluto by about 3 years. That is an astonishing trade. No enormous spacecraft engine had to produce that entire boost. No giant propellant tank had to be carried all the way from Earth solely to provide it. Mission designers arranged the geometry, so Jupiter itself became part of the trajectory. There is a subtle connection here to Ulysses. Both spacecraft used Jupiter, but they asked Jupiter for different things. New Horizons needed the giant planet to help it move outward faster. Ulysses needed the giant planet to help it move out of the solar system's plane. Same planet, different vector problem. For New Horizons, the central challenge remained energy and timing. The spacecraft had to reach Jupiter at the correct place, from the correct direction, so the encounter would produce the desired change in its sun-centered trajectory. After that encounter, Pluto was still billions of kilometers away. Yet most of those kilometers did not demand another giant acceleration. New Horizons continued outward. There were trajectory corrections. A real spacecraft is never launched with mathematical perfection, and tiny errors at the beginning can become enormous misses after years of travel. Mission controllers therefore made small adjustments when necessary. But compare the scale of those corrections with the scale of the journey. Near Pluto in 2015, one final correction burn lasted only seconds and changed the spacecraft's speed by only a fraction of a meter per second. The purpose was not to drive New Horizons across the remaining solar system. It was to refine where a spacecraft already moving on the correct interplanetary trajectory would arrive. This is the difference between propulsion and navigation. The enormous journey had already been purchased. The later burns corrected the aim. Imagine throwing a ball across a vast, perfectly frictionless landscape. If nothing resisted its motion, the difficulty would lie mainly in giving the ball the correct initial velocity. Making the landscape 10 times longer would make the wait longer, but it would not require 10 times as much force after release. Gravity makes the real solar system more complicated than that picture, but the central intuition survives. Distance is not fuel consumption. A well-designed orbit can carry a spacecraft through distance. This is why New Horizons could spend years crossing a region that would be impossible to traverse by continuously burning chemical rockets. It did not need to fight every kilometer. It needed the correct energy, the correct geometry, and the correct timing. And Pluto itself helped expose the weakness in our original distance-based intuition. New Horizons left Earth in 2006. It passed Jupiter in 2007. Then the dramatic events largely disappeared from public view. For years, the spacecraft crossed the darkness. The sun slowly weakened in the sky. Radio signals took longer to cross the expanding gap. Pluto remained ahead. But from the perspective of orbital mechanics, the long silence was not evidence that the spacecraft was struggling to move forward. The silence was the journey working. New Horizons was doing exactly what its launch and Jupiter encounter had arranged for it to do. Coast. By July 14, 2015, that trajectory carried it through the Pluto system, only thousands of kilometers above the dwarf planet's surface. 9.5 years of travel had delivered the spacecraft to a destination more than 3 billion miles along its voyage. And now the contrast with the solar polar mission becomes sharp. Suppose we made Pluto even farther away while preserving a workable outward trajectory. The travel time would grow. Communications would become harder. Power and reliability would become more demanding. The mission might become brutally difficult as an engineering project. But distance alone would not create the particular orbital penalty we are about to meet. A solar polar trajectory demands that we turn the velocity arrow itself through a large angle. And unlike coasting through another billion kilometers, that turn cannot be purchased simply by waiting longer. Now we are ready to see the bill. Now we can finally put a price on the turn. And the number is worse than distance ever suggested. Take the velocity arrow we have been carrying through this story. Near Earth's orbit, its length is about 29.78 kilometers per second. Suppose we want to change only the direction of that velocity. Not make the spacecraft faster, not make it slower, just rotate its path into a different orbital plane while keeping the same speed. Draw the original velocity as one arrow, then draw the desired velocity as a second arrow of equal length, tilted upward by some angle. The spacecraft begins with the first arrow. It needs to end with the second. The delta V is the difference between them, and simple geometry gives us the result. Delta V equals 2 times the speed multiplied by the sine of half the plane change angle. In symbols, delta V equals 2V sine delta I over 2. The equation is compact. Its consequences are not. Start gently. Imagine an instantaneous pure plane change of 10 degrees while moving at Earth's average orbital speed. Even that modest tilt requires a substantial change in velocity. Increase the turn to 30 degrees, and the idealized cost rises to about 15.4 kilometers per second. Pause on that number. 15 kilometers every second of velocity change, not to travel to Pluto, not to escape the solar system, and not to dive toward the sun. Just to rotate the direction of an orbit by 30 degrees while preserving roughly the same speed. Now increase the angle again. At 60 degrees, the required delta V becomes almost exactly equal to the original speed itself, about 29.8 kilometers per second. And then consider the cleanest version of the polar problem. A 90-degree turn. One velocity arrow lies in the ecliptic. The other points, perpendicular to it, both have the same length. At 29.78 kilometers per second, the instantaneous plane change would require roughly 42.1 kilometers per second of delta V. More than 40 kilometers per second simply to redirect the motion. That is the wall, hidden inside the title. But we need to be precise about what this number means. Ulysses did not perform a 42 km per second engine burn. No mission planner proposed taking a spacecraft moving with Earth's heliocentric speed and abruptly firing engines until its velocity rotated exactly 90 degrees while everything else remained unchanged. The calculation is an idealized reference case. Its purpose is to expose the geometry. It tells us what happens when we pretend that the easiest looking route on a diagram is also the route we should purchase directly with propulsion. The answer is brutal. And now we can see why. Return to the 2 arrows. If we wanted only to increase speed, we could add velocity in roughly the same direction as the first arrow. If we wanted only to reduce speed, we could add velocity in the opposite direction. But a large plane change requires building a new velocity that points somewhere substantially different. The old sideways motion does not disappear. It has to be countered by the change we apply. At 90 degrees, the new arrow is not merely one old arrow plus a small upward adjustment. The vector difference stretches diagonally between the tip of the old velocity and the tip of the new one. That diagonal is longer than either simple vertical component our intuition might first imagine. This is why saying, "we only need to go upward," is misleading. There is no universal upward in orbital mechanics. There is only a current velocity and a desired velocity. the spacecraft must bridge the difference. And the larger the angle between those velocities, the larger that bridge becomes. This gives us a much cleaner comparison with Pluto. New Horizons needed enormous launch energy. Its mission was not cheap in delta V, easy in engineering, or simple in navigation. But after departure and the Jupiter encounter had established the right outbound trajectory, another billion kilometers did not automatically demand another giant propulsive maneuver. Distance could accumulate during coast. A plane change cannot be accumulated in the same effortless way simply by waiting. If the spacecraft remains in an unperturbed heliocentric orbit, the orbital plane remains essentially the plane defined by its existing angular momentum. Time carries the spacecraft around that orbit. Time does not magically rotate the orbit toward the Sun's pole. Something has to change the vector. This is the deeper reason the solar polar problem is so different from the Pluto problem. One asks, in large part, how to put enough energy into the right outward trajectory. The other asks how to reorient motion that is already enormous. And there is another detail hiding inside the equation. Look again at it. Delta V equals 2 times the speed times the sine of half the angle. The angle matters, but speed is sitting there too, directly multiplying the cost. That means the same plane change becomes more expensive when we attempt it while moving faster. Turn a short velocity arrow through 30 degrees, and the difference between the arrows is relatively small. Turn a long velocity arrow through the same 30 degrees, and the gap between their tips grows. This is not an abstract mathematical curiosity. It is a mission design clue. If we cannot afford a large plane change, where the spacecraft is moving quickly, perhaps we should arrange for the turn to happen somewhere the relevant speed is lower. Or perhaps we should find an external force capable of redirecting the velocity for us. Now the route to Jupiter begins to look different again. At first, Ulysses travelling outward seemed absurd because its target was the Sun. Then Jupiter became a way to escape the flat track. Now we can see the size of the problem that forced that decision. The spacecraft needed a major change in orbital orientation. Trying to buy that change directly, near Earth's heliocentric conditions, would have demanded an extreme propulsive price. So mission designers did not pay it directly. They changed the circumstances. This is one of the recurring patterns of deep space navigation. When the required delta V is too expensive, do not immediately ask for a larger rocket. Ask whether the solar system contains a cheaper place, a slower point, a planetary encounter, or another physical process capable of changing the trajectory. Orbital mechanics rewards strategy. Sometimes the shortest geometric path is a terrible trajectory. Sometimes travelling farther first makes the eventual maneuver easier. And sometimes a destination in one direction is reached by deliberately beginning in another. The equation has now exposed the problem. A 30-degree change near Earth's orbital speed is already severe. A 60-degree change reaches almost 30 kilometers per second in our idealized case. A 90-degree turn rises to about 42. These are not Ulysses mission requirements. They are the geometry stripped bare. And the message underneath them is simple. Velocity direction is expensive. Very expensive when the existing velocity is large. So the next question almost asks itself. If turning an orbit is cheaper when the spacecraft is moving more slowly, where in the solar system should we try to make the turn? And if our engines cannot afford it, what else can bend the arrow? For Ulysses, those two questions pointed toward the same enormous answer. Jupiter. The cheapest place to turn is where you are moving slowly. That principle sounds almost obvious now. The plane change cost we just uncovered grows with speed, so if a spacecraft must rotate its orbit through a large angle, one strategy is to postpone that rotation until its heliocentric velocity is smaller. The solar system naturally provides places where that happens. Move outward. A spacecraft travelling on an elongated orbit around the Sun does not move at the same speed everywhere along that orbit. Near the Sun, it moves faster. Farther away, it moves more slowly. This is part of the same orbital behavior we see in planets and comets. As an object falls inward toward the Sun, gravity accelerates it. As it climbs outward, it gives up kinetic energy and slows. So imagine a spacecraft leaving Earth's neighborhood on a long elliptical path. Near Earth, its heliocentric speed is large. Farther from the Sun, near the outer end of that path, the spacecraft is moving more slowly. And suddenly the geometry from the last part changes. The velocity arrow is shorter. Rotate a shorter arrow through the same angle, and the delta V required for a pure plane change is smaller. This creates one of the stranger rules of orbital design. Sometimes it can be cheaper to travel a vast distance away from the place you ultimately care about, change your orbit there, and then return. The route is longer. The maneuver can be cheap. That sounds like cheating only because we are still tempted to measure difficulty in kilometers. Orbital mechanics measures something else. What velocity do you have at the moment you need to change it? This principle alone already suggests why the outer solar system might help a solar mission. But Ulysses had access to something even more powerful than a slower point in its orbit. There was a planet waiting there, Jupiter. And a planet can do something a coasting spacecraft cannot do by itself. It can bend the trajectory. Picture a spacecraft approaching Jupiter. Long before the encounter, the Sun still dominates the broad shape of the spacecraft's path, but as the distance to Jupiter shrinks, the giant planet's gravity becomes increasingly important. The spacecraft begins falling toward Jupiter. Its speed relative to the planet rises. Its path curves. It passes the planet, rather than striking it, swings through the gravitational encounter, and begins climbing away. If Jupiter were perfectly stationary in empty space, the basic encounter would not create free energy from nowhere. Relative to Jupiter, the spacecraft would approach and leave with essentially the same faraway speed in an ideal gravity assist. But something important would still have changed. Direction. The incoming path and outgoing path would not point the same way. Jupiter's gravity would have bent the velocity vector. Now place Jupiter back where it actually belongs. Jupiter is not stationary. It is orbiting the Sun. That means we have to look at the encounter from two different frames. Relative to Jupiter, the spacecraft falls in, curves around the planet, and escapes with its direction changed. Relative to the Sun, Jupiter itself carries an enormous orbital velocity. Combine Jupiter's motion with the spacecraft's redirected Jupiter relative velocity, and the spacecraft can leave the encounter with a substantially different heliocentric velocity vector. Its speed relative to the Sun may increase. It may decrease. Its direction may change. Often several things happen at once. That is the power of a gravity assist. The spacecraft is not producing the entire change with propellant carried from Earth. It is arranging an encounter so that a moving planet's gravity performs part of the transformation. The exchange is real. Momentum and energy are conserved. If a spacecraft gains heliocentric orbital energy from a planet, the planet loses an unimaginably tiny amount of its own orbital energy. Because Jupiter is so massive compared with a spacecraft, the planet's change is effectively imperceptible, while the spacecraft's change can be mission-defining. This is why calling a gravity assist a slingshot is useful but incomplete. A sling suggests speed. A gravity assist is really about vectors. The planet can reshape the spacecraft's trajectory. New Horizons use that ability in a way we have already seen. Its Jupiter encounter helped increase its outward heliocentric motion and shorten the journey toward Pluto. But a gravity assist does not have to be arranged only to make a spacecraft go farther or faster. Change the approach geometry, and the planet can redirect the spacecraft in another direction, including out of the ecliptic. Now we are approaching the heart of Ulysses. Before the Jupiter encounter, Ulysses was still traveling broadly within the planetary plane. It had not somehow climbed over the Sun during launch. It had been sent outward toward the giant planet. As it approached Jupiter, its heliocentric speed had fallen from the more extreme conditions near the inner part of its solar trajectory. Then came the encounter. Jupiter supplied the deep gravitational field. Mission designers supplied the geometry, and gravity supplied the bend. There is an important distinction here. Ulysses was not simply waiting until it moved slowly and then performing a conventional rocket-powered plane change. That would miss the most elegant part of the mission. Going outward helped place the spacecraft in a completely different dynamical environment, but Jupiter itself was the crucial lever. The spacecraft could enter the planet's gravitational field on one trajectory and emerge on another. No onboard engine had to reproduce the full vector change that the encounter created. This is why planets become part of a spacecraft's propulsion architecture, even though they are not engines. Their gravity can substitute for propellant, not without constraints. The spacecraft has to reach the planet has to be in the correct place, the approach angle has to be carefully designed. Closest approach cannot be chosen arbitrarily. A planet's atmosphere, rings, moons, radiation environment, navigation uncertainty, and the spacecraft's scientific requirements can all limit the geometry. And there is no universal gravity assist that produces any velocity vector we want. The laws of motion still decide what is possible. But within those laws, a planet offers a remarkable bargain. Instead of carrying enough fuel to force a huge trajectory change, use the motion and gravity already present in the solar system. This is a deeper way to think about interplanetary flight. A spacecraft does not merely travel through a collection of destinations. It travels through opportunities. Places where speed is lower, places where orbital energy can be exchanged, places where a moon or planet can turn a trajectory, places where a maneuver that would be punishing in one part of the solar system becomes manageable somewhere else. The shortest route through physical space may therefore be nowhere near the cheapest route through velocity space. And that is precisely the trap our title sets. Pluto seems harder because it is farther. The Sun seems easier because it is close. But Ulysses was not trying to cross the shortest distance to the Sun. It was trying to acquire an orbit whose direction Earth could not conveniently give it. So the mission went looking for leverage. It found that leverage hundreds of millions of kilometers in the wrong direction. There is still one final mental reversal before the route makes complete sense. We have been describing Jupiter as a useful way to solve an expensive plane change problem. That is true, but it understates what the mission designers actually accomplished. For Ulysses, Jupiter was not simply helping the spacecraft on its way to the Sun. Jupiter was doing the job that an impossibly demanding propulsion maneuver otherwise would have had to do. Once we see the encounter that way, the apparent detour disappears. Ulysses did not go to Jupiter before beginning its real route. Jupiter was the route. Jupiter was not a detour. It was the missing engine. Not literally an engine bolted to Ulysses. Of course, Jupiter burned no propellant for the spacecraft, but dynamically, the planet performed the job that an extraordinary onboard propulsion system would otherwise have needed to perform. It changed the direction of the spacecraft's motion so dramatically that Ulysses emerged from the encounter on a heliocentric orbit, inclined about 80 degrees to the Sun's equator. What had been a spacecraft traveling broadly with the planetary system became one capable of sweeping through the Sun's high northern and southern latitudes. That is the midpoint where our original map finally breaks. Until now, we have still been able to imagine Jupiter as an assistance along the route. It was more than that. Remove Jupiter from the mission, and you do not simply make Ulysses slower. You remove the mechanism that created the orbit the mission needed. The difference matters. New Horizons could use Jupiter to improve an already outward journey. Its basic objectives still belong to the outer solar system. Ulysses was different. Before Jupiter, the spacecraft had not yet acquired the defining geometry of its scientific mission. The encounter itself transformed the orbit from broadly ecliptic motion into the high-inclination solar trajectory that made the polar exploration possible. So imagine removing the planet. We still have a spacecraft near Earth's orbital plane. We still want an orbit tilted almost upright relative to that plane. And now we must ask the spacecraft to manufacture the transformation itself. That brings us back to the terrible numbers we uncovered earlier. Large delta V is not merely difficult because engines have to operate longer. For a rocket carrying its own propellant, additional delta V becomes progressively expensive because the vehicle must accelerate not only the spacecraft, but also the propellant that will be burned later. Propellant has mass. Accelerating that propellant requires more propellant. And accelerating that additional propellant requires still more. This feedback is built into the rocket equation. For a fixed propulsion system, the mass ratio required for increasing delta V grows exponentially rather than linearly. That is why a giant maneuver cannot usually be solved by saying, add a bigger fuel tank. The tank has mass. The extra fuel has mass. The structure supporting it has mass. The launch vehicle must accelerate all of it. At some point, the mission architecture itself has to change. Ulysses changed the architecture. Instead of carrying the entire solution, it traveled to a place where the solar system could provide one. Jupiter is exceptionally useful for this because it is enormous. Its gravitational field can bend a passing spacecraft's trajectory substantially when the encounter geometry is chosen correctly. Ulysses was sent toward the giant planet specifically so that the flyby could swing it out of the ecliptic and establish the high inclination orbit required for its solar observations. Now look at the mission from above the ecliptic. Ulysses leaves the inner solar system and heads outward. That still looks wrong. But rotate the viewpoint until we can see the system edge on. The spacecraft approaches Jupiter, still belonging largely to the thin planetary band. Then its path bends. After the encounter, it does not simply continue around the Sun on another flat ellipse. The entire orbital plane has changed. The flat track has been broken. This is the part ordinary distance maps cannot show. On a map measured only in kilometers, Ulysses traveled hundreds of millions of kilometers away from the Sun before beginning its polar survey. On a map of velocity vectors, it traveled to the place where the required transformation became possible. Those are two completely different definitions of a shortcut. The geometric shortcut points toward the Sun. The dynamical shortcut points toward Jupiter, and only one of them produces the orbit we need. There is an even deeper way to describe what changed. Every orbit has angular momentum. For our purposes, we can imagine its direction as another arrow, one pointing perpendicular to the orbital plane. Earth's orbital angular momentum direction points roughly out of the ecliptic. A spacecraft traveling in a similar plane begins with an angular momentum direction roughly aligned with it. To create a nearly polar solar orbit, that orientation must be tipped dramatically. So Ulysses was not merely changing where it would be a few months later, it was changing the orientation of the plane in which its future motion would unfold. Jupiter changed the geometry of years of flight in a single encounter. Afterward, Ulysses followed a long elliptical orbit around the Sun, inclined about 80.2 degrees to the solar equator, eventually reaching more than 80 degrees of solar latitude during its polar passages. This is why the word assist can almost sound too gentle. The planet did not merely save a little fuel, it enabled the defining trajectory, and that gives us a new interpretation of planetary gravity assists in general. A planet is not just something a spacecraft visits. Under the right geometry, it becomes part of the spacecraft's flight system. The launch vehicle supplies one part, the spacecraft's own propulsion supplies another. The Sun supplies the central gravitational field, and a moving planet can supply a trajectory change that would be painfully expensive to reproduce with onboard propellant. Mission design becomes less about overpowering gravity and more about arranging encounters with gravity. That is a profound change in strategy. The naive version of spaceflight says, determine where the target is, then build enough rocket to go there. Orbital mechanics says, determine what velocity you need, then search the solar system for the cheapest sequence of physical interactions capable of creating it. Sometimes that sequence looks direct. Sometimes it looks absurd. Ulysses belongs to the second category. Its scientific target was the Sun. Its crucial destination was Jupiter. And after the Jupiter encounter, the apparent contradiction disappeared. The spacecraft had finally gained what simply approaching the Sun could never give it: the right orbital orientation. From there, another surprise appears. Flying over the Sun did not mean flying especially close to it. Ulysses could reach extraordinary solar latitude while remaining much farther from the Sun than the spacecraft we now associate with extreme solar encounters. That distinction matters because we have been talking about two different axes of difficulty. One is getting inward. The other is getting upward. Parker's solar probe would eventually attack the first problem with extraordinary success. Ulysses attacked the second, and once those two missions are placed beside each other, the phrase "going to the Sun" becomes almost useless. There is no single journey to our star. There are different orbital problems hiding behind the same destination. Ulysses has now shown us the first one in full. To reach the Sun's poles, it did not overpower the flat architecture of the solar system. It recruited that architecture. It travelled outward. It borrowed Jupiter. It let gravity turn the arrow. And only then could it go over the Sun. After Jupiter, Ulysses entered a part of the solar system no spacecraft had explored before. Not because it had travelled farther than every earlier probe, because it had travelled sideways out of the map. The Jupiter encounter in February 1992 had placed Ulysses onto a long heliocentric orbit, tilted about 80 degrees to the Sun's equator. Instead of circling the Sun close to the plane occupied by Earth and the other planets, the spacecraft now cut steeply across it. For the first time, a spacecraft was on its way toward the Sun's polar environment. The journey was not immediate. After leaving Jupiter, Ulysses headed back toward the inner solar system while moving progressively further south of the ecliptic. By the middle of 1993, its instruments were already sampling a region increasingly dominated by conditions associated with the Sun's southern hemisphere. Then, on June 26, 1994, the formal South Polar observing period began. Ulysses crossed above 70 degrees south solar latitude. It continued climbing. 75 degrees. Then 80. In September, it reached about 80.2 degrees south. That is the geometry Jupiter had purchased. And notice what Ulysses was not doing. It was not skimming the solar surface. It was not flying through the corona. It was not approaching the Sun the way Parker's solar probe eventually would. During the polar passage, Ulysses remained far from the Sun, more than twice Earth's average distance from our star during portions of the southern survey. Yet its latitude gave it something no closer spacecraft confined near the ecliptic could provide: a new direction from which to sample the heliosphere. This was the scientific reason the orbital problem mattered. From Earth, and from most spacecraft travelling near the ecliptic, we naturally observe the Sun and solar wind from relatively low solar latitudes. That gives us a rich view of the equatorial and mid-latitude environment. But it leaves a question. Is the heliosphere really similar in every direction? Before Ulysses, we could build models. Ulysses could fly through the missing region. Its instruments did not need to take dramatic photographs of the poles to make the journey worthwhile. In fact, Ulysses carried no conventional imaging camera for producing close-up pictures of the solar surface. Its real landscape was invisible. Particles, magnetic fields, plasma, dust, radio waves, cosmic rays. The spacecraft moved through the material and fields flowing away from the Sun and measured them directly. And almost immediately, the polar environment began to look different. One of the clearest changes appeared in the solar wind. The solar wind is a continuous outflow of charged particles escaping the Sun's atmosphere and spreading through the solar system. Near Earth, its properties can vary considerably as different solar regions rotate into view. Above the southern polar region during this relatively quiet phase of the solar cycle, Ulysses encountered something different. The wind was fast and comparatively smooth. Measurements from the solar wind experiment showed flow from the polar region moving substantially faster than the wind commonly sampled near the solar equatorial environment. That was more than an interesting number. It told scientists that the heliosphere had large-scale structure with latitude. The solar system was not sitting inside a simple spherical wind blowing outward identically in every direction. There were different regimes. The poles mattered. Then came the magnetic field. Researchers had expected the magnetic field measured in the solar wind to become stronger as Ulysses climbed toward high latitude. The spacecraft did not see the expected increase. Instead, the measured field strength remained surprisingly uniform from lower latitudes toward the pole. That forced scientists to reconsider aspects of the models connecting the Sun's surface magnetic field with the magnetic field carried outward by the solar wind. This is what the strange orbit was buying. Not merely a record. A test. From inside the ecliptic, scientists could infer what might be happening above the Sun. Ulysses could place instruments there. The spacecraft also detected strong magnetic fluctuations associated with waves traveling through the fast polar solar wind. And another expectation weakened. For years, scientists had considered whether the geometry of the Sun's polar magnetic field might provide an easier route for galactic cosmic rays to penetrate toward the inner solar system. If such a polar funnel existed in the simple way expected, Ulysses should have detected a strong rise in cosmic ray intensity as it climbed toward the pole. It did not. The increase was small. Another attractive picture had failed the direct test. That pattern matters to our larger story. First, the mission trajectory defeated intuition. Now the science was doing the same thing. The obvious route to the Sun's poles had been wrong because distance was not the governing variable. And some of the obvious expectations about the polar heliosphere were wrong because measurements from the planetary plane had not told the complete story. Changing perspective changed the answer. By November 1994, Ulysses had descended below 70 degrees south latitude again. But the first polar experiment was only half complete. The spacecraft continued along its steep orbit toward the Sun's equatorial region. In March 1995, it crossed the solar equator. Around the same time, Ulysses reached the closest point to the Sun on that orbit, roughly 200 million kilometers away. Even at perihelion, it remained farther from the Sun than Earth does. Then the spacecraft kept climbing. This time north. On June 19, 1995, Ulysses entered the northern polar observing region above 70 degrees latitude. Again the numbers rose. 75, 78. Finally, at the end of July, about 80.2 degrees north. The spacecraft that had once been launched from a planet locked near the ecliptic had now passed from one solar polar region to the other, south to north. For the first time, scientists could compare high-latitude conditions across both hemispheres using the same spacecraft and the same instruments. By the end of the northern pass in September, Ulysses had completed the first pole-to-pole survey of the Sun's environment. More than 3 billion kilometers of travel had gone into creating that perspective. But the scientific prize was not the distance. It was the third dimension. Until Ulysses, much of our direct sampling of interplanetary space had effectively followed the solar system's broad disk. Ulysses turned that disk into a volume. It measured how solar wind speed, magnetic fields, energetic particles, cosmic rays, and other properties changed as latitude changed. And the results showed why going above the Sun had been worth such an awkward route. The heliosphere did not look the same from every latitude. The poles were not simply the equator viewed from another direction. They were part of a structured, changing system whose global form could not be reconstructed completely from one thin slice. This is the quiet payoff of all the orbital mechanics we have built so far. The velocity arrows were not abstract mathematics. The Jupiter encounter was not trajectory trivia. The 80-degree inclination was not a number added for spectacle. Every one of those engineering choices existed because the science required access to a region that Earth could not naturally provide. Ulysses had changed the direction of its orbit, and by doing that, it changed the direction from which humanity could investigate the Sun. But this creates one more important distinction. Ulysses reached extraordinary solar latitude while remaining surprisingly far from the Sun. Another spacecraft would eventually do almost the opposite. It would stay much closer to the broad planetary plane, yet fall deeper toward the Sun than anything humanity had ever built. That spacecraft was Parker's solar probe. Put Parker beside Ulysses, and the phrase "hard to reach the Sun" splits into two completely different problems. One is the battle to get above. The other is the battle to get close. But Ulysses never got especially close to the Sun. That sounds wrong after everything we have just watched it accomplish. The spacecraft flew over the solar poles. It reached latitudes no previous mission had reached. It transformed our view of the heliosphere from a thin equatorial slice into a three-dimensional system. Yet even at the closest point in its orbit, Ulysses remained about 200 million kilometers from the Sun, roughly 1.3 times the average Earth-Sun distance. Earth itself is closer to the Sun than Ulysses was at perihelion. That fact reveals the next trap in the phrase "flying over the Sun." High latitude and close distance are not the same achievement. They are different coordinates of an orbit. Imagine that we have two large dials controlling a spacecraft's path around the Sun. The first changes the size and shape of the orbit. Turn it one way and the perihelion drops inward. Turn it the other and the orbit stretches outward. The second dial tilts the entire orbital plane. Ulysses turned the second dial dramatically. Its orbit stood almost on edge compared with the familiar planetary plane. But the first dial was not turned far enough inward to make Ulysses a close solar probe. Its orbit still carried it from about 1.3 astronomical units at perihelion to more than 5 astronomical units near aphelion. That was not a failure. It was the mission design. Ulysses was built to sample the Sun's environment across latitude. Its instruments measured particles, magnetic fields, plasma waves, cosmic rays, dust, and the solar wind as the spacecraft moved through regions that no earlier probe had directly sampled. It was not designed to produce dramatic close-up pictures of the solar poles. In fact, Ulysses carried no imaging instruments for that purpose. This is why saying that it flew over the poles can create the wrong mental picture. We may imagine a probe passing directly above the solar surface, looking down at a blazing polar cap from close range. Ulysses did something subtler. It occupied an orbit whose geometry carried it to extreme solar latitudes, allowing it to sample the heliosphere above and below the Sun while remaining comparatively distant from the star itself. The word "over" describes direction, not closeness. And that distinction gives us a better way to think about every solar mission. There is no single scale marked "how much did this spacecraft reach the Sun?" A spacecraft can go close without going far north or south. It can go far north or south without going especially close. It can change orbital energy. It can change orbital inclination. It can attempt both. Each choice asks for a different transformation of the velocity vector. This is the part that ordinary mission comparisons often blur. If we compare spacecraft only by closest distance to the Sun, Ulysses does not look extreme at all. If we compare them by solar latitude, it becomes extraordinary. Now reverse the comparison. Parker Solar Probe has passed only about 3.8 million miles above the solar surface. At closest approach, it has moved at roughly 430,000 miles per hour, faster than any other human-made object. By proximity and speed, Parker occupies a completely different regime from Ulysses. But Parker did not reproduce Ulysses' near-polar orbit. It solved another axis of the problem: inward. This is where the two-dial picture becomes useful. Ulysses made a huge change to orbital orientation by using Jupiter, Parker made a huge change to orbital energy. By repeatedly using Venus as mission design, used 7 Venus gravity assists, culminating in the trajectory that brought Parker to its record close solar passes. One spacecraft went outward to gain the geometry required to climb. The other repeatedly encountered an inner planet to lose enough heliocentric orbital energy to fall deeper. Both routes look inefficient if distance is the only thing we measure. Both become elegant once velocity becomes the map. And now we can sharpen the title even further. When we say that flying over the Sun can be harder than reaching Pluto, we are not claiming that every imaginable spacecraft passing above the Sun requires more total mission capability than every possible Pluto mission. We are isolating a specific orbital demand. Starting from Earth, producing a very large solar inclination is extraordinarily expensive if we try to do it directly. Pluto is vastly farther away, but it lies broadly within the flattened family of solar system motion. A spacecraft can receive a high-energy outward trajectory and then allow gravity and time to carry it across much of the distance. A polar solar trajectory asks us to rotate the architecture of the orbit itself. Ulysses proved the solution, but it also exposed the compromise. We could obtain extreme latitude by borrowing Jupiter's gravity, yet the resulting orbit did not take the spacecraft down into the environment immediately above the solar surface. To combine those two achievements would mean solving 2 hard problems at once. First, remove enough heliocentric angular momentum and energy to drive the orbit inward. Then also acquire enough out-of-plane motion to raise the inclination, or arrange some sequence of planetary encounters, repulsion, or continuous low-thrust forces that can gradually do both. That is a much harsher trajectory problem. It also explains why the first spacecraft to fly over the solar poles did not give humanity the first close photographs of those poles. The geometry that made Ulysses scientifically unique did not make it a close-range camera platform. For years, the polar surface itself remained difficult to see directly from above. The accomplishment was not smaller because of that limitation. It was more precise. Ulysses answered a particular question. What is the Sun's environment like when we finally leave the plane in which almost every planet and spacecraft naturally travels? Parker would answer another. What happens when we finally remove enough of Earth's inherited sideways motion to plunge into the Sun's outer atmosphere? Those questions sound related because both missions are called solar probes. Orbital mechanics keeps them separate. One asks us to turn, the other asks us to brake, and the solar system charges differently for each. This is the mental model we need from this point forward. Do not picture a single road leading toward the Sun. Picture a space of possible orbits. Some are flat and wide, some are flat and narrow, some stand steeply against the ecliptic. A mission is difficult not because its destination sits at one particular distance, but because of how far its required orbit lies from the orbit we start with. Earth gives us one starting state. Every ambitious mission is an attempt to transform it. Ulysses transformed the direction. Parker transformed the depth. And if Ulysses showed us why going above the Sun can require a journey to Jupiter, Parker is about to show us something equally strange. Even when the Sun is pulling on you with all its gravity, falling toward it is still not easy. Because before Parker could fall inward, it had to lose the motion that kept making it miss. Parker's solar probe had to slow down before it could become the fastest spacecraft ever built. That sounds contradictory. It is the entire mission in one sentence. Earth begins with roughly 67,000 miles per hour of sideways motion around the Sun. Parker inherited that motion at launch. To drop deep into the solar gravitational well, it had to remove a large fraction of it rather than simply point toward the Sun and accelerate. NASA estimates that the mission needed to shed about 53,000 miles per hour of that inherited sideways motion to reach its intended solar encounters. The Sun was already pulling Parker inward. The problem was that Parker kept moving sideways. So the mission became an exercise in braking. Not once. Repeatedly. Parker Solar Probe launched on August 12, 2018, aboard a Delta IV Heavy, one of the most powerful launch vehicles available for the mission. Yet even that launch could not simply cancel Earth's heliocentric motion and place Parker immediately into its final close solar orbit. The required change was too large. The spacecraft needed Venus. Less than 2 months after launch, on October 3, 2018, Parker made its first Venus gravity assist. The geometry was arranged differently from the Jupiter encounter that accelerated New Horizons toward Pluto. Parker passed Venus in a way that reduced its speed relative to the Sun. During that first encounter alone, Venus lowered Parker's heliocentric speed by roughly 7,000 miles per hour, about 10%, and pulled the perihelion of the spacecraft's orbit around 4 million miles closer to the Sun. One encounter, a smaller velocity arrow, a deeper orbit. Then Parker came around again. This is where the mission design becomes almost musical. Parker falls inward. It races around the Sun. It climbs outward again. Venus moves around its own orbit. At the correct future moment, spacecraft and planet meet once more. Another gravity assist alters Parker's heliocentric trajectory. The orbit tightens. Parker returns to the Sun on a deeper path. Then the cycle repeats. 7 Venus gravity assists were built into the mission architecture, rather than using one enormous planetary encounter to create a polar orbit, as Ulysses had done at Jupiter. Parker used a sequence of smaller encounters to progressively reduce its perihelion while remaining near the ecliptic. NASA's trajectory history traces this architecture to mission designer Yang-Ping Guo, who in 2007 developed alternatives to earlier solar probe concepts that relied on traveling all the way to Jupiter. That was a major change in philosophy. Earlier concepts had considered Jupiter because the giant planet could perform an enormous transformation. It could slow a solar probe dramatically and throw it into a steep orbit that returned toward the Sun. But that architecture came with costs. Years of deep space travel, power challenges near Jupiter, limited time near the Sun, and a trajectory strongly connected to polar passes. The Venus solution traded that dramatic single transformation for repetition. Smaller planet, smaller assists, more encounters, more solar passes. Parker would not climb over the Sun the way Ulysses had. Instead, it would keep returning to the inner solar environment again and again. NASA's mission design projected more than 900 hours inside 20 solar radii, compared with less than 100 hours for earlier Jupiter-based concepts. That trade reveals something important about the word harder. Orbital mechanics rarely asks only whether a trajectory is possible. It asks what kind of mission the trajectory creates. A Jupiter route could provide a huge change. A Venus sequence could provide repeated close encounters. The final architecture was chosen not merely to reach a number on a distance chart, but to create a scientifically useful pattern of orbits. And each Venus encounter pushed Parker farther from the orbit Earth had originally given it, not further in distance, farther in orbital state. The energy dropped. The perihelion descended. The spacecraft entered regions where the Sun occupied more of the sky and where the solar atmosphere was less processed by millions of kilometers of expansion. Then comes the apparent contradiction. If Parker was repeatedly slowing relative to the Sun, why does it become so extraordinarily fast near perihelion? Because braking is what allows the fall. When Venus removes orbital energy from Parker, the spacecraft can no longer remain on the previous wider solar orbit. Its new trajectory reaches deeper into the Sun's gravitational potential well. As Parker falls inward, gravity accelerates it. Potential energy becomes kinetic energy. The deeper Parker falls, the faster it becomes near the bottom of the orbit. So the mission uses planetary gravity to slow the spacecraft at the right places, then solar gravity accelerates it to extraordinary speed later. Slow down. Fall deeper. Speed up. There is no contradiction once we separate the different locations along the orbit. It is the same basic principle that makes a comet accelerate as it approaches the Sun and slow as it recedes. Parker simply manipulates the shape of that orbit deliberately. By November 6, 2024, the sequence reached its final Venus gravity assist. Parker passed only 233 miles, or 376 kilometers, above Venus's surface. That encounter placed the spacecraft into the orbital configuration that would produce its record solar approach the following month. Then, on December 24, 2024, Parker passed approximately 3.8 million miles above the Sun's surface. Its speed near closest approach reached roughly 430,000 miles per hour. The spacecraft had become the fastest human-made object in history precisely because its trajectory had first been engineered to lose the sideways orbital energy that once prevented it from falling so deeply. That is the Parker paradox. We remove speed from the orbit, so gravity can give us much more speed near the Sun. And Parker has continued returning to that same extreme orbital regime. On June 8, 2026, it completed its 28th close solar approach, again reaching roughly 3.8 million miles from the surface and matching the same record speed. But look carefully at what Parker did not solve. Its record has almost nothing to do with escaping the solar system's flat architecture. Parker went inward with extraordinary success. It did not become a Ulysses-like polar spacecraft. This brings our two dials back into view. Ulysses changed the orientation dial. Parker changed the depth dial. Jupiter turned one spacecraft out of the planetary plane. Venus helped another spacecraft tighten its orbit around the Sun. The same technique, called a gravity assist, served two fundamentally different pieces of velocity geometry, and the contrast becomes almost beautiful. New Horizons used Jupiter to gain outward energy. Ulysses used Jupiter to gain orbital inclination. Parker used Venus to lose orbital energy. 3 missions, 3 desired velocity vectors, 3 different uses of moving planets. Distance alone would never tell us why their trajectories look the way they do. Velocity does. Parker also gives us one final correction to the idea of falling into the Sun. The Sun's gravity is immense. But gravity cannot simply erase angular momentum. If a spacecraft begins with enough sideways motion, gravity bends that motion into an orbit rather than dragging the spacecraft straight inward. To reach the inner corona, Parker needed the solar system itself to help remove that obstacle, encounter by encounter. That is why getting close to the Sun took years of orbital choreography, even after the spacecraft had already left Earth. But now we have seen 2 extremes. Ulysses reached almost over the poles while remaining comparatively distant. Parker reached extraordinarily close while remaining broadly within the familiar planetary plane. The next mission begins to connect those worlds. It does not yet climb to anything like Ulysses' 80-degree latitude. It does not fall as deeply as Parker. Instead, it is slowly changing both the view and the geometry, using repeated encounters with Venus to tilt its orbit farther and farther above the ecliptic. And in doing so, Solar Orbiter has begun giving humanity something Ulysses never could. Actual views of the Sun from above its poles. Solar Orbiter does not fly directly over the Sun. Not yet. And that is exactly what makes it useful to our story. Ulysses showed what could happen when a spacecraft sacrificed closeness for an extraordinary change in orbital inclination. Parker Solar Probe showed what could happen when a spacecraft sacrificed high latitude for an extraordinary plunge inward. Solar Orbiter occupies the territory between them. It approaches the Sun much more closely than Ulysses did. It carries telescopes capable of imaging the solar surface and atmosphere, and instead of trying to jump immediately into an 80-degree orbit, it is climbing away from the ecliptic gradually, one encounter with Venus at a time. The climb is modest by Ulysses standards. But in March 2025, 17 degrees was enough to change the view. For almost the entire history of solar astronomy, humanity observed the Sun from close to its equatorial plane. Earth lives there. Most planetary spacecraft live there. Even powerful observatories that watch the sun continuously see its poles at a shallow angle. The poles remain near the edge of the disk. Features become compressed. Magnetic measurements become harder to interpret. Motion toward or away from us becomes difficult to separate from motion across the surface. Then Solar Orbiter moved below the familiar plane. On March 23, 2025, the spacecraft viewed the Sun from about 17 degrees below the solar equator. That is nowhere close to looking straight down from 90 degrees. But it was enough. For the first time, a spacecraft equipped to image the Sun could directly see its south polar region from outside the ecliptic plane. The distinction with Ulysses could hardly be cleaner. Ulysses had reached more than 80 degrees of solar latitude decades earlier, but it carried no imaging telescopes designed to photograph the solar surface. Solar Orbiter climbed only a fraction as far out of the plane of, yet it brought eyes. 3 instruments were especially important in those first polar observations. The Polarimetric and Helioseismic Imager, or PI, observed the visible surface and mapped magnetic fields. The Extreme Ultraviolet Imager revealed million-degree plasma in the corona, and the SPICE spectrograph separated light from material at different temperatures in the solar atmosphere, allowing scientists to study both structure and motion. The result was not a single conventional photograph. It was several physical layers of the same unexplored region. Surface, magnetism, corona, moving plasma. For the first time, the polar geometry was becoming something we could image rather than only sample while flying through it. And immediately, the Sun refused to look simple. Measurements of the south polar magnetic field showed patches of both magnetic polarities mixed together. That was not necessarily a permanent property of the pole. Solar Orbiter had arrived during a particularly revealing phase of the solar cycle, when the Sun's global magnetic field was in the process of reversing. Roughly once during each 11-year activity cycle, the Sun's large-scale magnetic polarity flips. Near that transition, the polar magnetic field can become disordered before a dominant polarity eventually emerges again as the Sun moves toward minimum activity. Solar Orbiter was looking directly into that changing region while the transformation was underway. That matters because the poles are not decorative ends of a rotating star. They are deeply connected to the Sun's magnetic cycle. The magnetic fields transported toward the polar regions help shape the large-scale field that will exist during the next phase of solar activity. Understanding that evolution is therefore tied to understanding why the Sun moves between relatively quiet periods and periods filled with sunspots, eruptions, and powerful disturbances in space. From near-Earth orbital plane, scientists can study enormous amounts of solar magnetism. But the viewing geometry near the poles has always been difficult. Solar Orbiter is changing the geometry instead of asking the data to compensate for it. That is the recurring trick in this entire story. When the perspective is physically wrong for the measurement you need, move the spacecraft. But moving the spacecraft is the hard part. Solar Orbiter did not suddenly fire its engines upward by 17 degrees. Venus did the lifting. A February 18, 2025 gravity assist increased the spacecraft's orbital inclination from roughly 8 degrees to about 17 degrees. The same planet that Parker used to lower orbital energy was now being used by another mission to increase orbital inclination. Same gravity, different geometry. Again, this is one of the cleanest proofs that a gravity assist is not simply a speed boost. Parker encountered Venus in geometries designed primarily to make its solar orbit smaller. Solar Orbiter encounters Venus in geometries that progressively rotate its orbital plane. The planet is not deciding what happens. The trajectory is. And Solar Orbiter is not finished climbing. It remains at roughly 17 degrees during its present orbital phase. The next planned Venus encounter, on December 24, 2026, is designed to raise the inclination to about 24 degrees. Later Venus flybys are planned to push the angle higher still, eventually reaching about 33 degrees from 2029. Each step improves the polar view. But even 33 degrees is nowhere near Ulysses' roughly 80-degree geometry. That difference prevents us from turning Solar Orbiter into something it is not. It is not a replacement for a true overhead polar spacecraft. Its achievement comes from combining a meaningful out-of-ecliptic view with remote sensing instruments and relatively close approaches to the Sun. That combination is scientifically powerful. Ulysses could move through the polar heliosphere and directly measure the particles and fields surrounding the spacecraft. Solar Orbiter can connect conditions in space with structures visible on the Sun itself. A plume seen in ultraviolet light can be compared with magnetic structure beneath it. Spectroscopy can reveal whether material is moving toward or away from the spacecraft. Those observations can help researchers investigate how material begins escaping into the solar wind and how the polar atmosphere changes through the solar cycle. So our two orbital dials are no longer merely an analogy. Mission history is turning both of them. Parker turns the depth dial hard. Ulysses turned the inclination dial hard. Solar Orbiter turns both more moderately, trading the extremes for a different kind of scientific connection. And that trade tells us why there has never been one perfect trajectory to the Sun. Every orbit gives something up. Go extremely close and thermal protection, speed, communications, and orbital energy become severe constraints. Go extremely polar using Jupiter and the trajectory grows large and distant. Try to obtain useful closeness and useful latitude together, and the orbital architecture becomes a long sequence of carefully timed compromises. The interesting question is therefore no longer whether humanity can see the Sun's poles. We already have. The harder question is how far we can push that geometry. Could a future spacecraft climb much higher while remaining close enough to image the polar surface in extraordinary detail? Could it watch the same pole continuously rather than sweeping past it? Could it follow the magnetic field through an entire solar cycle from a vantage point that Earth can never provide? To do that, gravity assists may not be enough. A planet can only help when the spacecraft can reach it, at the correct time, with the correct geometry. Venus offers repeated opportunities, but every encounter changes the orbit by a limited amount. Jupiter can produce a far larger turn, but it sends the mission into a radically different architecture. Eventually, another method becomes attractive. Instead of changing the orbital plane in a few violent gravitational encounters, what if we could apply a tiny force continuously? Not for minutes, for months, for years, a force that required no conventional propellant at all. The sunlight pouring outward from the very star we are trying to observe can provide exactly that kind of pressure. And if we can learn how to lean against it correctly, the Sun itself may become the tool that finally carries a spacecraft toward a truly polar orbit. The Sun may eventually solve the problem it created, not with gravity. With light, every photon leaving the Sun carries momentum. When sunlight strikes a reflective surface and changes direction, some of that momentum is transferred to the surface. The force is tiny. But in space, tiny forces can become powerful if they never stop. That is the idea behind a solar sail. Instead of carrying propellant and throwing mass backward through a rocket engine, a spacecraft unfolds an enormous, extremely lightweight reflective sheet. Sunlight pushes against it continuously. No conventional propellant is consumed to produce that thrust. NASA describes solar sailing as continuous photon pressure propulsion, capable of accumulating large velocity changes over long periods, precisely because the acceleration can continue for months or years. At first, this sounds like the wrong technology for our problem. Sunlight travels outward. We are trying to climb above the Sun. But a sail does not have to face sunlight straight on. Tilt it. The reflected photons leave in a different direction, and the force on the sail changes direction with them. Part of the acceleration can then point sideways relative to the Sun spacecraft line, change the sail orientation carefully as the spacecraft moves around its orbit, and that small lateral force can gradually reshape the trajectory. Now return to the velocity arrow. Chemical propulsion tries to change that arrow quickly. Jupiter changed Ulysses' arrow dramatically during one encounter. A solar sail offers another strategy. Do not turn the arrow all at once. Nudge it. Again and again, orbit after orbit. The force during any single moment may seem almost meaningless, but the spacecraft does not have to carry fuel for every future nudge. As long as sunlight reaches the sail and the vehicle can maintain the required orientation, photon pressure keeps providing acceleration. Time becomes part of the propulsion system. This is almost the opposite of the large plane change burn we imagined earlier. That idealized 90-degree maneuver asked for an enormous velocity change immediately. Solar sailing asks whether we can accumulate the required change gradually. Instead of fighting the orbital plane in one violent event, we slowly crank the plane upward. NASA engineers have studied exactly this possibility. One concept is called the High Inclination Solar Mission. It is not an operating spacecraft or an approved mission whose flight is guaranteed. It is a mission concept designed to test what near-term solar sail technology might make possible. Its target geometry is striking. The studied trajectory first spirals inward until the spacecraft reaches a roughly circular orbit at about 0.48 astronomical units from the Sun. Then the real climb begins. The sail repeatedly produces an out-of-plane component of acceleration, increasing the orbital inclination at rates reaching roughly 10 degrees per year in the concept study. The eventual goal is greater than 75 degrees of heliographic inclination. 75 degrees. Now compare that with everything we have seen. Solar Orbiter is presently working from roughly 17 degrees and is planned to climb higher through future Venus encounters. Ulysses reached about 80 degrees, but only after traveling all the way to Jupiter and returning on a vast orbit. The solar sail concept aims for Ulysses-like high latitude from a much tighter orbit around the Sun. That combination is the prize. High and close. The two dials we separated earlier would finally be turned together. One NASA solar polar imager study examined a circular heliocentric orbit at 0.48 astronomical units and 75 degrees inclination, using a sail area of about 7,000 square meters. NASA's high-inclination solar mission studies likewise use solar sailing because the sustained delta-V requirement is beyond practical conventional chemical propulsion and extremely challenging even for highly efficient electric propulsion. 7,000 square meters is not a normal spacecraft appendage. It is a structure, a surface large enough that mass, stiffness, deployment, pointing, wrinkling, thermal behavior, and control all become major engineering problems. This is the catch. Solar sailing does not make orbital mechanics disappear. It changes which problem we have to solve. The propulsion equation becomes friendlier because the sail does not consume a tank of propellant every time it produces thrust. But the spacecraft must carry an enormous lightweight surface and control it with extraordinary precision. Sunlight pressure is weak, so useful acceleration demands large area and low mass. And because the thrust direction depends on the sail's orientation, navigation and attitude control are inseparable from propulsion. A sail that points incorrectly does not merely look the wrong way, it accelerates the wrong way. NASA is already testing pieces of that technology in space. The Advanced Composite Solar Sail System launched in April 2024. Its sail is about 80 square meters, supported by lightweight composite booms, and NASA lists the demonstration as active. The mission is testing technologies for deploying larger sails and using sail orientation to change an orbit. That spacecraft is nowhere near the scale of the high-inclination concepts we have just described. And that difference matters. An 80 square meter technology demonstrator does not prove that a 7,000 square meter scientific sail can be built, deployed, controlled, and operated for years close to the Sun. The engineering gap remains real, but the physical principle is no longer hypothetical. Sunlight can propel spacecraft. Sail angle can control the direction of that propulsion, and sustained photon pressure can alter an orbit without spending conventional propellant for each accumulated velocity change. This brings us back to the strange hierarchy of solutions in our story. New Horizons used chemical launch energy and Jupiter to stretch outward. Ulysses used Jupiter to rotate dramatically upward. Parker used repeated Venus encounters to move inward. Solar Orbiter is using Venus to climb gradually while staying close enough for detailed imaging. A future solar sail could add another option: continuous inclination change, no single giant turn, no mandatory journey to Jupiter, just years of almost imperceptible acceleration, patiently rotating the orbit. And there is something fitting about that. The obstacle began with Sunlight's star. Earth formed inside a rotating disk around the Sun. We inherited an orbit inside that disk. Every spacecraft launched from Earth begins with that same broad directional commitment. The Sun's gravity keeps us moving within it. Then photons from the Sun offer a possible way out. Not by overpowering the velocity we inherited in one enormous maneuver, by changing it slowly, degree after degree, orbit after orbit. This is why solar sailing is more than an exotic propulsion technology in this story. It attacks the exact quantity that made the title surprising. Delta V. A chemical spacecraft carries a finite reserve of it. A gravity assist borrows it from planetary motion, but only when the geometry provides an encounter. A solar sail can keep accumulating velocity change as long as the mission can keep using sunlight effectively. The acceleration is weak. The persistence is the weapon. And that opens a possibility Ulysses could only hint at. A spacecraft high above the Sun, but still close enough for sustained, detailed observation. Not a brief crossing from south to north. Not a distant sampling pass. A platform capable of watching polar magnetic fields evolve, seeing the corona from a radically different perspective, and following structures that are badly foreshortened from Earth. NASA studies have even examined solar sail architectures reaching a full 90-degree solar polar orbit at roughly 0.48 astronomical units, although such studies remain mission concepts rather than promises of future flight. That distinction is important. We have not solved the polar problem. We have identified a physically credible path that could change how it is solved. And the path reinforces the lesson running through every mission in this story. When orbital mechanics gives us an impossible-looking bill, the answer is rarely to ignore the bill. Change how we pay it. New Horizons paid with launch energy and Jupiter. Ulysses paid with a planetary turn. Parker paid through repeated encounters with Venus. A future polar sail might pay one photon at a time. And now every piece is in place. We know why Pluto's distance is misleading. We know why Earth gives us the wrong motion for a polar orbit. We know why turning that motion directly is so expensive. We know why Ulysses had to travel outward before it could rise. And we know why even today's most ambitious solar missions still treat inclination as something precious. Only one question remains. When we strip away every spacecraft name, every gravity assist, and every equation, what is the simplest answer to the title? Why, in the physics of the solar system, can flying over the Sun really be harder than reaching Pluto? The answer is that Pluto is farther away, but the Sun's poles require a more radical change in motion. That is the whole mystery. Distance made the comparison look impossible. Velocity makes it obvious. A spacecraft does not begin its journey from rest somewhere outside the solar system. It begins on Earth, already moving around the Sun at nearly 30 kilometers per second, already embedded in the broad plane where the planets travel, already carrying a large amount of orbital angular momentum in a particular direction. That starting condition matters more than the number of kilometers printed beside the destination. Pluto is extraordinarily far away. but its orbit still belongs broadly to the flattened architecture of the planetary system. A spacecraft leaving Earth for Pluto can use much of the motion it already possesses. The launch vehicle adds energy. The heliocentric orbit stretches outward. Jupiter can add more energy and reshape the trajectory. Then gravity and time carry the spacecraft across billions of kilometers. The journey is long. The engineering is severe. But the spacecraft is not being asked to completely reinvent the orientation of its orbit. Flying over the Sun is different. To pass through the Sun's high latitudes, a spacecraft must leave the plane that gave it its original motion. The important change is not simply more speed. It is a new direction. That means changing the velocity vector itself and, with it, the orientation of the spacecraft's orbital angular momentum. This is why the flat track has mattered throughout our story. Earth gives every departing spacecraft a powerful head start. But a head start is useful only when it points roughly toward the orbit we want. For Pluto, much of that inherited motion is useful. For a polar solar orbit, much of it becomes something we have to redirect. And redirection is expensive. The idealized plane change calculation exposed just how expensive. At Earth's heliocentric speed, even a 30-degree instantaneous change in orbital plane would demand a huge delta V. At 60 degrees, the required change becomes comparable to Earth's entire orbital speed around the Sun. At 90 degrees, the simple equal speed reference case rises to roughly 42 kilometers per second. Again, that is not the burn Ulysses performed. It is the warning hidden in the geometry. Trying to rotate a fast heliocentric velocity vector directly is an awful way to build a polar orbit. So Ulysses did not try. It went to Jupiter. That journey is the clearest answer to the title because it demonstrates the difference between physical distance and orbital difficulty in a real mission. If the Sun were merely hard to reach because of distance, sending a solar spacecraft hundreds of millions of kilometers outward first would make no sense. But Ulysses did not need the shortest path to the Sun. It needed access to a different orbit. Jupiter supplied the leverage. The spacecraft approached the giant planet broadly within the familiar planetary plane. Jupiter's gravity bent its velocity vector dramatically. After the encounter, Ulysses emerged on a heliocentric orbit tilted roughly 80 degrees to the Sun's equator. The mission had gone outward to acquire the ability to go upward. That is not a paradox anymore. It is orbital mechanics. And it reveals why the word harder needs to be used carefully. New Horizons launched from Earth faster than Ulysses did. Parker Solar Probe eventually traveled far faster than either spacecraft near the Sun. A mission can be harder thermally, harder operationally, harder to communicate with, harder to keep alive for decades, or harder to launch. Those are different comparisons. The specific difficulty in our title is the orbital transformation required to reach high solar latitude from an Earth-like starting orbit. On that measure, distance alone tells us almost nothing. What matters is delta V. More precisely, what matters is the difference between the orbit we have and the orbit we need. That is the deeper rule. A destination in space is not merely a position. It is a position plus a velocity. If we arrive at the correct location with the wrong velocity, we have not necessarily reached the orbit we wanted. This is why spacecraft do not navigate through the solar system the way ships cross an ocean. A ship can broadly point toward a location and keep supplying propulsion. A spacecraft is usually trying to enter a particular gravitational trajectory. Once that trajectory is established, enormous distances may pass beneath it almost for free. But changing from one trajectory to another costs something. Sometimes rockets pay. Sometimes planets pay. Sometimes sunlight may eventually pay. The currency is still velocity change. Parker Solar Probe proved the same idea from another direction. The spacecraft wanted to go close to the Sun rather than high above it. That did not require a giant inclination change. It required losing enough heliocentric orbital energy that Parker could fall into a much tighter orbit. Venus repeatedly helped remove that energy. Then solar gravity accelerated Parker to record speed near perihelion. Parker therefore solved the inward problem. Ulysses solved the upward problem. And New Horizons solved the outward problem. Put the three trajectories together, and physical distance becomes almost secondary. New Horizons gained energy and stretched outward. Parker lost energy and fell inward. Ulysses redirected the orbital plane. Three spacecraft leaving the same planetary neighborhood. Three different transformations. That is why the solar system cannot be understood as a simple map of near and far. Its real geography is made from motion. There are easy directions and expensive directions. There are velocity vectors we inherit and velocity vectors we must manufacture. There are places where a planet can provide leverage and places where no useful planet happens to be waiting. There are trajectories that look wasteful in kilometers, but efficient in delta V. And there are trajectories that look short on a diagram but become punishing once we calculate what the spacecraft must do to its existing motion. Flying over the Sun belongs to that last category. On paper, the destination appears close. The Sun is right beside us on the scale of the solar system. But the polar orbit is far away in velocity space. Pluto is almost the reverse. It is physically remote beyond ordinary intuition. Yet its direction lies much closer to the broad dynamical road on which Earth is already travelling. That is why a spacecraft can receive enough energy, coast outward for years, and eventually arrive at Pluto, without continuously fighting the geometry of the solar system. And that is why a spacecraft intended to reach the Sun's poles may have to travel toward Jupiter before the real solar mission can even begin. The kilometers were never the decisive obstacle. The orbit was... So if we want the shortest possible answer to the title, it is this. Reaching Pluto mainly asks us to stretch an orbit outward. Flying over the Sun asks us to rotate an orbit out of the plane. Stretching can work with much of the motion Earth already gives us. Rotating must overcome or redirect that motion. And when the inherited velocity is nearly 30 kilometers per second, changing its direction can cost more than traveling billions of kilometers along the path it already wants to follow. That resolves the physics. But one realization remains. The empty solar system we see in photographs is crossed by no visible roads, no rails, no walls, and no boundaries. Yet spacecraft behave as though some directions are open highways and others are steep mountains. To understand why, we need to look one last time at the flat track beneath Earth. Because the strangest thing about the road to Pluto is that part of the journey begins before any rocket leaves the ground. Before any spacecraft leaves Earth, part of its journey has already been chosen. Not its destination, its direction. Earth is moving around the Sun at nearly 30 kilometers per second, carrying everything on its surface with it. Every rocket, every telescope, every probe begins inside that motion. For most of our lives, we never notice it. The ground feels still. The Sun appears to cross the sky. The planets seem to hang against the stars. But underneath that familiar experience, Earth is racing along an ancient path inherited from the disk that formed the solar system more than 4.5 billion years ago. That path is the flat track we have followed through this story. It has no rails, no edge, no surface. Nothing marks it in empty space. Yet it shapes almost every mission we launch. And this is the final realization. The solar system has directions that are naturally easier to travel because we are already moving in them. That is the hidden advantage behind the journey to Pluto. Pluto is unimaginably distant by human standards. New Horizons needed years to cross the gap. Radio signals took hours to reach the spacecraft. The Sun became smaller. Earth became effectively invisible. But New Horizons did not begin from stillness. Earth had already given it a tremendous sideways velocity around the Sun. The launch vehicle added to that motion and reshaped it. Jupiter added more. Then the spacecraft coasted. Year after year, the kilometers accumulated. Mars's orbit passed behind, then Jupiter, then Saturn's distance, then Uranus, then Neptune, finally Pluto. The distance was enormous, but the trajectory had been purchased much earlier. This is why the long silence of an interplanetary cruise can be deceptive. Nothing spectacular may appear to be happening. No continuous pillar of rocket exhaust drives the spacecraft onward. There is no engine fighting through every kilometer. The spacecraft simply follows the orbit created for it. Gravity does the rest. Time does the rest. The motion it already possesses does the rest. In that sense, some of the road to Pluto exists before the spacecraft even launches. It exists in Earth's velocity. Now turn 90 degrees away from that road. There is the other journey, the Sun's poles. Physically, they are nearby compared with Pluto. Dynamically, they lie in a direction Earth does not naturally give us. That is why the problem feels so strange. We can send spacecraft billions of kilometers outward because enormous distance can be crossed by staying broadly within the family of motion we inherit. But to climb over the Sun, we must leave that family. We have to turn the arrow. Ulysses showed us what that means better than any equation could. A spacecraft built to study the Sun left Earth and headed outward toward Jupiter. That sentence should still sound slightly wrong, but now we know why it was right. Jupiter was where the orbit could be transformed. The giant planet bent Ulysses away from the planetary plane and placed it on a trajectory that carried it through the Sun's high latitudes. The route looked longer in kilometers. It was shorter in the only geometry that mattered. Velocity space. That idea reaches beyond Ulysses. Parker's solar probe showed another version of it. The Sun's gravity was always strong enough to pull Parker inward. Gravity was not the missing ingredient. Parker's sideways motion was the obstacle, so Venus repeatedly helped reduce its orbital energy. Only then could Parker fall deeper, and the deeper it fell, the faster the Sun accelerated it. The spacecraft that had to slow down became the fastest spacecraft ever flown. Solar Orbiter reveals the same logic more gradually. It uses Venus not simply to gain or lose speed, but to climb out of the familiar observing plane step by step. The mission is teaching us that even modest changes in viewing latitude can reveal parts of the Sun that Earth cannot easily show us. And perhaps future solar sails will continue the process without waiting for a planet to provide each turn. A tiny pressure from sunlight, sustained for years, may eventually rotate an orbit toward the poles, degree by degree. Different spacecraft, different technologies, different centuries of exploration. The same underlying rule. We do not travel through the solar system by defeating distance. We travel by transforming motion. That may be one of the least intuitive facts about spaceflight. Human beings evolved in a world where location dominates navigation. If something is nearby, we expect it to be easy to reach. If something is far away, we expect it to be difficult. That instinct works beautifully when we walk across a room or cross an ocean. In orbit, it can fail completely. A nearby destination may require an enormous change in velocity. A distant destination may lie almost naturally along a trajectory we can enter once and follow for years. The map of the solar system therefore has two layers. One is the map we see. Kilometers, planets, orbits, distances from the Sun. The other is invisible. Velocities, angular momentum, orbital energy, inclinations, places where gravity can add something, places where gravity can remove something, places where an orbit can be turned more cheaply than somewhere else. That invisible map is the one spacecraft actually obey, and once we see it, many strange missions stop looking strange. Going to Venus before approaching the Sun, passing Jupiter on the way to Pluto, flying all the way to Jupiter to reach the Sun's poles. None of these routes are mistakes or elaborate detours. They are consequences of beginning the journey from a moving Earth. Perhaps that is the most beautiful part of orbital mechanics. A spacecraft never really asks, where is the destination? It asks something closer to, what path can nature give me from the motion I already have? Then engineers search for an answer. A rocket burn here, a planet there, a long coast, a carefully timed encounter. Perhaps one day, a sail leaning almost imperceptibly into sunlight. The spacecraft does not force its way through the solar system. The best trajectories cooperate with it. They borrow gravity. They borrow planetary motion. They borrow time. And sometimes they travel enormous distances in order to avoid one expensive turn. So when we look at Pluto and the Sun, the obvious hierarchy disappears. Pluto is not easy. The Sun's poles are not impossibly remote. Those categories were built from the wrong measurement. The real comparison begins with Earth, with the velocity we inherit, with the thin planetary plane in which that velocity lies, with the difference between the orbit beneath us and the orbit we want. That is why the deepest lesson of this journey is not really about Pluto, and it is not really about the Sun. It is about the fact that motion has memory. Earth remembers the disk from which it formed through the orbit it still follows. Every spacecraft we launch inherits a piece of that memory. We can increase it, reduce it, bend it, borrow another planet to transform it, but we cannot pretend it is not there. And once we understand that, the strange road through the solar system becomes quiet and clear. Pluto may lie billions of kilometers farther away, but it waits broadly along the road Earth is already traveling. The Sun's poles lie almost next door. We simply are not moving that way. And that is why flying over the Sun can be harder than reaching Pluto,